What's up, science fam? In the last video, we talked about earthquakes and how we measure them, how we determine the epicenter, the faults, whose fault it is, and so on. And in this video, we're going to talk about the seismic waves. My name is Sir Ramon, and this is Science with Sir Ramon, with part 2 of earthquakes. So let's get right into it. If earthquakes release seismic energy, how does this turn into actual seismic waves? So we can investigate that through seismology, or the study of seismic energy. Now, why would we study seismic energy? What are seismic waves like? How can we even begin to describe energy that's flowing like ripples through the earth? So different seismic waves have different kinds of shake. Different seismic waves can shake and cause land to shake differently as they travel. So as these waves ripple out, they move land or they move matter in different ways. And that allows us to classify or categorize your different seismic waves. So there are different waves, and we can classify them into two main categories. We have the surface waves and the body waves. Let's just move my face so you can read properly. So the surface waves are the waves that travel on the Earth's surface. Duh! So we have here the surface waves. Again, they just go on the Earth's surface. They don't go deeper than that. What does go deep are the body waves. So they travel through the body of the Earth or the Earth's interior. So there are two types of waves each in these big categories. On surface waves, we have Love and Rayleigh waves. In body waves, we have P waves and S waves. So let's start with the body waves. So the body waves are waves that go through the body of the Earth. And we have two types, again, P wave and S wave. The first, the P wave, also known as the primary wave, is the fastest type of seismic wave. That's why it's called the primary wave, because it's the first thing that seismographs detect. Now, P waves are also responsible for the parallel movement of matter as it travels. By parallel, we mean same direction. So, as the wave travels, matter also gets compressed and expanded or moved in the same direction. So, if the wave is propagating all the way in that direction, matter also gets moved in that general direction. It gets compressed and expanded in the direction that the wave is traveling, like an accordion or a slinky. Again, P waves, parallel compression and expansion, and it's the fastest type of seismic wave. Your S wave, or the secondary wave, is the second fastest. That's why it's secondary. And the difference is that it's perpendicular. It uses what we call shear forces. So again, shear forces, S-H-E-A-R. These are forces that cause a perpendicular movement of matter, meaning it's up and down. If the wave is moving towards this direction, follow my cursor, the perpendicular movement of the ground or the matter will be up and down. So it's at a 90-degree angle with how the wave is actually moving. So it's like a rope or a whip. When you whip your rope or your towel, so it has a up and down motion that travels in a certain direction. So that's your S wave. Next are your surface waves. So we just discussed the body waves. The surface waves are waves that travel on the surface, the ones we can actually feel during an earthquake. The first is the love wave. And then just like love, it's the most destructive type of wave. Why? Because love waves will move your particles or your matter side to side, just like that Ariana Grande song. So in love waves, again, it moves side to side, causing structures like buildings to also move and sway side to side. Now in the videos we watched in the warm-up activity, that's really dangerous because things tend to fall over and fall on people, stuff like that. So again, love waves are the most destructive waves, and they're called love waves because it was discovered with a guy whose last name was Love. It has nothing to do with the abstract concept of love, even though that's also destructive. Next, we have the Rayleigh waves. It's the most felt wave, the wave that we can perceive the easiest as observers, because Rayleigh waves have a rolling motion. So your particles or your matter rolls with the wave. So if you look at a particular cube or square, as the wave rolls through this GIF image, you can see they're actually just rolling in place. So they roll right, left, up, down, and then back in place. So it's most felt, but it's not as dangerous as love waves because things still end up just going back to where they belong. Alright? Again, your matter generally just rolls around and then goes back to its proper position. So even though we feel it, it doesn't actually cause a lot of damage. It still does though. So it's a rolling wave, your Rayleigh wave. So why should we study these though? Why do we have seismology? What makes it good to understand these aside from understanding earthquakes? So these seismic waves actually help us find out more about Earth's interior, or the body of the Earth. So only seismic waves can be used to study the interior of the Earth, because we can't drill into the Earth very, very well. The deepest we've ever gone is in the Kola super deep borehole in Russia. So Soviet Russia tried to do that. They only went through a part of the crust, and it didn't even get that far through the crust. So it's very difficult to study Earth's interior. But seismic waves travel differently depending on what they're traveling through. So the properties of the matter they're traveling through will make them travel in a different way. So based on that, it gives us clues on what the layers of the Earth are. So in particular, your P wave and your S wave, your body waves, have different properties. Your P waves can pass through both liquids and solids. So the solid and liquid layers of the Earth will allow the P waves through. So what happens is that seismographic locations that detect seismic energy, can detect these P waves at almost every part of the Earth. So even if the epicenter is on the other side of the world, there are still some P waves that are detected on the opposite end of the world. However, we have what we call shadow zones. So these shadow zones give clues that these P waves are being bent out of the way. So instead of going straight through the Earth and to these parts of the Earth on this side, they get bent as they go through different layers of the Earth with different properties. So again, once it hits a different layer, it gets bent or refracted so that it causes a shadow zone of P waves. Your S waves, on the other hand, can only pass through the solid layers. So your S waves, the black arrows, will propagate only through solid. So when there's a liquid layer will completely stop your S waves from propagating, meaning you won't detect any S waves beyond that liquid circle or liquid layer of the Earth. So putting together all the clues, if we put together all the clues from how P waves and S waves refract, it gives us an idea of the layers of the Earth and the boundaries of the layers of the Earth. It also gives us an idea of the composition, because your speed of the seismic waves will depend on what the layers are made of. So depending on what they're made of, your speed of the waves will either increase or decrease, making it bend in different ways. So what are they then? If it gives us an idea about layers and boundaries, what are these layers and boundaries? So sit tight, we're going to go through them one by one. So this is the structure of the Earth. However, there are two ways. So there are two sides to this. There's this side and there's that side, and we're going to discuss both of them. So two ways to describe the structure of the Earth. There's the compositional way. So everything on this left side is a compositional way of talking about the Earth. If you zoom in, it says consists of. So it's based on what it's made of. The structural, on the other hand, is based on the physical characteristics, or how these layers behave. Alright, so let's go through this one by one. Let's get rid of my face. So the outer layer of the Earth, we have the crust. For the compositional description, we have the crust. It's the thin, solid shell. So if we think of the Earth as an egg, it's the egg shell. Now your crust is made up of oceanic crust and continental crust. Your oceanic crust is more dense than the continental crust. On the other hand, your lithosphere is the layer of the Earth, the structural layer of the Earth, that is made up of things that are rigid. Again, if it's rigid and is on the outer surface of the Earth, it's called the lithosphere. So this includes the crust, what's defined by this term, the crust, as well as the upper mantle, the rigid upper mantle. So it considers how the upper mantle behaves like an elastic solid. So since the upper mantle is very rigid and very solid, it's still considered part of the lithosphere. On the other hand, we have the mantle. So just beneath the surface, we have the mantle. It's a compositional description. So again, on this side, the composition. The mantle is a significantly less dense layer of the Earth. So it acts like a viscous fluid over a period of geological time, and it's mostly consisting of ultramafic silicates. You don't need to remember that, but again, it's based on the composition of the layer. So next we have, on the structural side of things, the asthenosphere and the lower mantle. So again, the same layer The mantle can be described as the asthenosphere and the lower mantle. The asthenosphere is partially molten and it's plastic. When we say plastic, it means it's solid, but over a long geological time scale, it still flows as if it was liquid. So again, it's technically solid based on physical properties, but it flows. It has enough energy and it has enough molten parts, enough molten volume to flow like a plastic solid. Your lower mantle, on the other hand, is more rigid than the asthenosphere, so it doesn't flow much. So that's the structural definition of your mantle. So the deepest parts of the Earth, the compositional deepest part is the core. It's the center of the Earth, and it consists of magnetic metals. On the other hand, if we look at it structurally, the outer core is actually liquid, and that's what prevents your S waves from propagating to the other side of the Earth. Again, liquids stop S waves, and that's in your outer core. Now, your outer core moves slowly around the inner core. Your inner core is a solid magnetic ball. So because of the solid magnetic ball in the center and the spinning outer core, also made up of magnetic metals, it functions like your electromagnets. So if you've ever had an experiment in physics where you have a nail, an iron nail, and then you wrap it with wire, and then you have electricity running through the wire and it becomes a magnet, that's the same as the Earth. The Earth is like a giant electromagnet. We have that nail, the inner core, and then we have that wire with electricity flowing through it, the outer core that's moving. So that creates an electromagnetic field that shields us from solar radiation. So thank you, inner and outer core. So next we have the boundaries between these layers. Again, these boundaries would not have been discovered without the seismic waves changing their speed because of these discontinuities. So these boundaries are called discontinuities, and we have 5. We have the Conrad discontinuity. It's between the upper and the lower crust. But you don't really need to remember that. So again, you can forget Conrad. Let's focus on the Mohorovicic. It's so complicated to spell and to pronounce that even scientists call it the Moho layer. The Moho discontinuity is between the crust and the mantle. So again, the properties of your P waves and your S waves change at this particular discontinuity. It's called the Moho discontinuity. Beyond that, we have the Repeti discontinuity. It's between the upper and the lower mantle. It describes the boundary between the asthenosphere and the lower mantle. Next, we have the Gutenberg discontinuity. It describes the boundary between the lower mantle and the outer core. Again, between the mantle and the core. Your Leman discontinuity, finally, is between the outer and the inner core. So again, your properties of waves changes at these discontinuities or these boundaries between the layers. So basically, it's not all bad. Sometimes things like seismic waves, which can cause bad times in terms of earthquakes, big disasters, sometimes they help us learn more and help us do better in the future because we are more informed about things. So again, PHIVOX, the local seismological agency in the Philippines, they can't predict earthquakes, but what they learn about earthquakes in the past and in history allows us to better prepare for them in the future. Alright, so if you have any questions, you can ask me on our Edmodo group or in Messenger. This concludes our lecture videos for this week. I'll see you guys in the next topic. See ya.